All right, let's get into it. Today, we're going to crack open one of the greatest geological detective stories of all time. It's a fantastic tale about a radical idea, a puzzle the size of a planet, and a discovery that completely flipped our understanding of the very ground beneath our feet. You know, it all starts with something you've probably noticed yourself, just staring at a world map. Have you ever seen how the big bulge of Africa seems to just nestle perfectly into the curve of South America? Well, that's not just a coincidence. That's clue number one in our mystery. For a long, long time, that little observation was just a curiosity, a weird, that's neat. But it turned out to be the first thread you pull that unravels this massive, planet-sized puzzle that had the world's best scientists just scratching their heads. Yeah, the fit of the continents was really just the tip of the iceberg. The more that scientists looked, the more they found these bizarre, almost ghost-like connections linking lands that were separated by thousands of miles of ocean. And the evidence was just baffling. I mean, how could there be ancient scars from glaciers in the hot deserts of Africa? And get this, the fossils. Mesosaurus was a small freshwater reptile. There is no way it could have swum across the entire Atlantic Ocean. Same story for the land dweller, Lystrosaurus. And the plant Glossopteris? Its seeds were way too heavy to be carried by the wind across such enormous oceans. It just didn't make a lick of sense. So how in the world do you explain all these impossible connections? Well, back in the early 20th century, a German meteorologist, of all people, named Alfred Wegener, came up with a really bold, almost unthinkable explanation. Wegener called his big idea continental drift. He proposed that all the continents we know today were once slammed together into this giant supercontinent he named Pangaea. And suddenly, it all clicked. The fossils matched up, the glacier scars connected, the coastlines fit together, because millions of years ago, they were all one piece. It explained everything. Well, almost everything. As brilliant and, as elegant as Wegener's idea was, it was met with some serious rejection from the scientific community, because his otherwise perfect theory had one giant fatal flaw. This was the question that stumped everybody. Wegener could show that the continents had moved, but he couldn't explain how. I mean, what kind of incredible force would be powerful enough to literally push solid continents through the Earth's crust? To most scientists, it just seemed impossible. So, without that missing mechanism, that how, Wegener's theory was pretty much ridiculed and put on a shelf to collect dust. The case of the wandering continents officially went cold for nearly half a century. The case went cold for decades. Then, this unexpected breakthrough came from the darkest, most hidden place on Earth, the deep ocean. New tech that came out of World War II, like sonar, let scientists do something they'd never done before, actually map the huge, secret landscape of the ocean floor. And what they found down there was about to change everything. Snaking its way around the entire globe like the seam on a baseball, they discovered the Mid-Oceanic Ridge. It's the longest mountain chain in the world. And this wasn't just some geographical feature. It turned out to be the very engine that was driving the continents. The answer they found was a process called seafloor spreading. Okay, so think of it like a giant conveyor belt for the entire planet. You've got molten rock constantly welling up from the Earth's mantle right at that ridge, creating brand new ocean floor. As this new floor forms, it shoves the older floor out to the sides, carrying the continents along for the ride. This was it. This was Wegener's missing mechanism, finally found. But science demands proof, right? And the final, undeniable evidence, the absolute smoking gun that proved seafloor spreading was real, was found locked inside the rocks themselves, in the form of a magnetic barcoe. This is where a field called paleomagnetism comes in. When volcanic rock cools and solidifies, tiny magnetic minerals inside it line up with the Earth's magnetic field, like trillions of microscopic compass needles. Then they get locked in place, preserving a perfect snapshot of the magnetic field at that very moment in time. Now here's the really wild part. Earth's magnetic field isn't stable. Every few 100,000 years or so, it completely flips. North becomes south and south becomes north. So rocks that form during a normal polarity period, like we have today, point north, while rocks formed during a reversed polarity period actually point south. So as new crust is constantly being made at the mid-ocean ridge, it's recording these magnetic flips over millions and millions of years. The ocean floor essentially becomes this giant, slow-moving magnetic tape, documenting the planet's entire magnetic history and its rocks. And just to give you a sense of the timescale we're talking about, the last time our planet's magnetic field did this whole flip-flop was about 780,000 years ago. We've been in our current normal period, what scientists call a crone, ever since then. So when scientists towed magnetometers across the ocean, this is what they found. It wasn't some random mess. It was a perfect mirror image pattern of magnetic stripes on either side of the ridge. Normal, reversed, normal, reversed. A geological barcode. This was the slam dunk, undeniable proof that the seafloor was spreading from the center, pushing the continents apart. With this discovery, the case was just blown wide open. All the pieces finally fell into place, and it triggered an absolute revolution in our understanding of the Earth. That great mystery that had stumped Wegener, the thing he was ridiculed for, it was finally solved. The continents weren't plowing through the crust itself was moving, and the continents were simply along for the ride. So let's close the case file. Wegener's original clues, the fossils, the glaciers, the puzzle piece fit, they established that a crime had happened. The continents had moved. The mid-oceanic ridge was the scene of the crime. Seafloor spreading was the method, the how, the missing mechanism. And that magnetic barcode on the ocean floor, that was the fingerprint, the undeniable proof that closed the case and gave birth to the modern theory of plate tectonics. And the story isn't over. This process is happening right now as we speak. The Atlantic Ocean is getting wider, the Pacific is shrinking. Which leaves us with one final fascinating question. If this is our world today, what's it going to look like in the deep future? Where are the wandering continents headed next?
All right, today we're going on a bit of a treasure hunt. We're diving deep into the Earth's crust to find the hidden treasures that, and this is no exaggeration, literally build the world around us, metallic ores.
So think about it for a second. The phone in your pocket, the car you drive, the biggest buildings in our cities, what could they possibly share? They seem like they're from different worlds, but they all share a common ancestor, something forged deep inside the planet.
Yep, the answer is metals. But here's the thing, you can't just go outside and pick up a chunk of aluminum or iron. Getting these materials involves a massive, worldwide search for very specific kinds of rocks, and that's where the real treasure is.
So what is it that turns a totally ordinary rock into a priceless treasure? Well, to answer that, we have to get into what an ore actually is. Okay, the official definition sounds a little academic, I know. But there are two words in there that are absolutely key: concentration and economically. It's not enough for a metal to just exist in a rock. It has to be packed in there tightly enough and be valuable enough to make it worth all the trouble of digging it up.
Let's break that down. For any rock deposit to be called an ore, it's got to pass three big tests. First, is there enough in it? That's quantity. You need a big pile. Second, what's the quality like? Is there a high enough percentage of metal in the rock? Geologists call this the grade. And third, is it actually worth anything? Is the price of that metal high enough to justify the cost of mining? That's value.
So, this is the most important takeaway. An ore isn't just a geological term, it's an economic one. You could have a mountain full of low-grade copper that's basically worthless one day, but if the price of copper suddenly doubles, boom, that worthless rock just became a treasure trove. And get this, technology changes the game too. A new, cheaper way to extract metal can instantly turn what was once just a big hill into a valuable ore. It's this constantly shifting dance between geology, money, and tech.
All right, now that we know how to spot a treasure, let's open the vault. Welcome to the Hall of Treasures, where we're going to meet some of the heavy hitters, the metals that really shape our modern world.
You know, looking at this table is like reading the DNA of modern civilization. Iron from ores like hematite, that's the steel that makes up the skeleton of our skyscrapers. Aluminum from bauxite is why we can build things that are both strong and light, like airplanes. Copper from chalcopyrite, well, that's the nervous system of our world, the wires that carry our electricity and data. And yep, even that heavy battery in your car comes from lead, found in galena. Every single one of these is a critical link in the chain of our entire industrial world.
Okay, take a look at this number, 95%. Just let that sink in for a second. What single metal do you think is so dominant that it makes up 95% of all the metal we use by weight on the entire planet?
The answer, and this chart just says it all, is iron. It is the undisputed king. By weight, it makes up 95% of every piece of metal humanity uses, mostly because it's the main ingredient in steel. Think about that.
All those other super important metals we just talked about, aluminum, copper, gold, you name it, they all have to squeeze into that tiny little 5% sliver. It's just staggering.
So we know iron is king, but how did these incredible deposits of metal get so concentrated in the first place? Well, the Earth itself acted like a series of giant forges, using unimaginable heat, pressure, and time to create these natural treasures. Let's look at the 4 main ways it happens.
Our first forge takes us deep, and I mean deep, underground. We're talking about massive, churning chambers of molten rock, or magma. This is the world of magmatic processes.
The easiest way to think about this is like a big bottle of salad dressing. You shake it up, but when you let it sit, the heavy stuff settles to the bottom, right? It's the same idea here. As a giant blob of magma cools over thousands of years, the really heavy, metal-rich minerals literally sink and collect at the bottom of the chamber. This forms these incredibly rich, layered deposits of metals like nickel and copper.
Okay, next up is a process that's kind of like a planet-sized plumbing system. It's called hydrothermal circulation, and it's all about super hot, mineral-rich water.
So picture this. Boiling hot water forces its way through cracks in the Earth's crust. As it travels, it acts like a solvent, dissolving tiny little bits of metal from the surrounding rock. When that hot water eventually cools down, it can't hold on to the metals anymore, so they drop out and get deposited. This is also how we get one of the most alien-looking things on Earth, those black smoker vents on the deep ocean floor. They're like underwater geysers, just belching out superheated, black, metal-rich water that builds up into these huge chimneys of pure metallic minerals. They're literally treasure chests being formed right before our eyes. Our third forge isn't about heat, it's about chemistry. And for this one, we have to jump in a time machine and go back billions of years to a time when the Earth's oceans and atmosphere were totally different from today.
Billions of years ago, the oceans were just full of dissolved iron. Then something amazing happened. Tiny little organisms figured out photosynthesis, and they started pumping a brand new toxic gas into the atmosphere, oxygen. This oxygen dissolved in the oceans and did what oxygen does best to iron. It made it rust. All that iron literally rusted out of the seawater and rained down onto the seafloor, layer after layer, for millions of years. This created the massive banded iron formations that provide almost all of the iron we use today. It's incredible. A single biological event gave us the raw material for the entire industrial revolution.
And finally, our last process happens right up here on the surface. It's powered by things we can see every day, like rivers and erosion. We're talking about placer deposits.
This is basically nature's own version of panning for gold. Seriously, as mountains wear down over time, heavy, tough minerals like gold and platinum get washed into streams and rivers. The moving water is strong enough to wash away all the lighter sand and gravel, but the super dense gold and platinum just drop. They get left behind and concentrated in places like the inside bends of a river. This is the original classic treasure hunt.
So, we've seen how nature creates and hides the treasure. Now let's look at how the modern hunt for it plays out in the real world, because this is where geology smashes right into economics and environmental science.
First, let's look at the Flambeau mine in Wisconsin. This was a massive sulfide deposit born from one of those ancient black smokers. But what's really mind-boggling is the grade here, an average of 9.5% copper. That is unbelievably rich. In just 4 years, it produced a staggering amount of copper. But here's the key part. It's since been completely mined out and the land has been fully reclaimed, turned back into nature. It's a powerful example of the full life cycle of a modern mine.
Now, contrast that with a very different story, the proposed Pebble Mine in Alaska. This is a whole different beast. It's a low-grade deposit. To make money, the mine would have to be one of the largest open-pit mines on the planet. And it just so happens to be located at the headwaters of one of the world's most important salmon fisheries. This single project perfectly captures the modern challenge. Our undeniable need for these metals versus the huge environmental questions that come with digging them up on such a massive scale.
And this quote really just hits the nail on the head. Every major mining project in the world today is this same high-stakes balancing act. The treasure is definitely in the ground, but the hunt forces us to ask some really tough questions about what we value most and what price we're ultimately willing to pay. And all this leaves us with one final massive question. We've built our entire technological civilization on these hidden treasures, but the high-grade, easy-to-find deposits, they're finite. They won't last forever. So what happens when the treasure map runs out? It's a question that's going to push us to do some incredible things, like perfecting recycling, so-called urban mining, or maybe even looking to asteroids for our metals. But it's the question that will define the next chapter for all of us. Thanks for joining this explainer.
All right, let's dive in. Imagine the Earth is a master chef, and it's got this ancient, incredible cookbook. Today, we're going to flip through the pages and look at the amazing recipes our planet uses to cook up the resources that literally build our world.
I mean, really, have you ever stopped to think about it? This stuff doesn't just show up at the store. It's the end result of these epic geologic processes that have been simmering away for millions and millions of years. So today, we're going to trace it all back to the source.
Now, before we get to the really wild recipes, like any good chef, we've got to understand our basic ingredients. So let's just get a few key terms straight.
First up, a mineral resource. This is the big, broad category. Just think of it as finding a pocket of something useful in the Earth's crust. It's a concentration of stuff that we could potentially pull out and use. But see, not all resources are worth the effort. That brings us to ore. And the magic words here are at a profit. You can find gold anywhere, but if it costs you more to dig it up than the gold is actually worth, well, it's not an ore. Simple as that.
And finally, we get even more specific with reserves. This is the stuff we've not only found, but we have the tech and the money to get it out of the ground profitably right now, today. It's the stuff that's actually on the books, ready to go.
Okay, with our terms down, let's head to the main kitchen, the Earth's mantle. This is where the real, high-heat, high-pressure cooking happens.
Our first recipe is called magmatic segregation. So picture a giant underground chamber full of molten rock, magma. As it slowly starts to cool, the heaviest minerals, things like chromite and magnetite, they turn solid first. And just like heavy chocolate chips sinking to the bottom of cake batter, these dense crystals sink and collect into these super concentrated layers.
And the scale of this is just staggering. Get this, the Bushveld complex in South Africa was formed this exact way. The result? It holds over 70% of the entire world's known platinum reserves. 70% in one geologic formation. Now that is one seriously rich cake.
Okay, let's move on to our next recipe from the mantle. And this one is all about pure, raw speed. We're talking kimberlite pipes. You can just think of them as the express elevator for diamonds. And I mean express. Diamonds form under insane pressure, like 450 kilometers down. These kimberlite eruptions are so violent and so fast that they literally blast the diamonds to the surface in a geologic blink of an eye. They have to be that fast, otherwise the diamonds would just turn back into boring old graphite on the way up. It's an absolutely incredible ride from the deep earth.
All right, let's move out of the deep mantle for a bit and look at a different kind of cooking, something more like a pressure cooker. This recipe uses superheated, mineral-rich water to get the job done.
So this process creates two main kinds of deposits. On one hand, you have vein deposits. This is probably what you picture, right? Hot water flows into cracks in the rock, cools down, and leaves behind these beautiful veins of minerals like gold and silver. Then you have disseminated deposits. Instead of a solid vein, the mineral grains are spread all throughout the rock, kind of like sprinkles mixed into a cake. This is how we get most of our copper.
And when I say most of our copper, I mean it. This right here is the Bingham Canyon mine. It is so enormous you can literally see it from space. Every single bit of copper in that massive hole was put there, tiny grain by hot water flowing through rock millions of years ago. Just mind-blowing.
Okay, so we've been deep inside the hot kitchen. Now let's come up to the surface, where the chefs are just wind and rain. Believe it or not, these weathering processes can create some seriously valuable resources. Let's talk about bauxite. This stuff is the one and only source of all our aluminum. How does it form? Well, in super rainy tropical climates, the constant downpour basically washes away everything else from the soil, leaving behind this thick, concentrated layer of aluminum-rich clay. Next up is a recipe that is all about sorting things out. We call them placer deposits, and they're basically nature's sieve. So a rock with heavy minerals inside it breaks down. It gets washed into a river. The water is strong enough to carry away all the light sand and gravel, but the really heavy, dense, valuable minerals, they get left behind, concentrated in the riverbed. So what kind of minerals are we talking about here? Oh, just the really valuable ones? This process is the reason for every single gold rush in history. Prospectors panning in rivers were just collecting the gold that nature had already sorted for them.
And it doesn't just work for gold, but also for other heavy hitters like platinum and even diamonds. So far, we've focused a lot on the shiny metals and the pretty gems, but this last chapter in our cookbook, you could argue it's the most important one for our day-to-day lives. We're talking about the non-metallic resources, the literal building blocks of our civilization.
I mean, just look at how fundamental this stuff is. You've got limestone, the key ingredient for cement, gypsum, which makes the wallboard in our houses, sylvite, which gives us the potassium for the fertilizer that grows our food. They aren't flashy, but these are the true unsung heroes of the Earth's cookbook. The modern world simply doesn't exist without them. So we've just seen these amazing, powerful, and incredibly slow recipes that the planet uses to create resources. Recipes that take millions of years of heat and pressure and sorting. And here we are, using them up on a timescale of minutes and days. It leaves you with a pretty big question, right? Which one of these ancient planetary recipes will be completely impossible for us to ever recreate? Something to think about. Thanks for watching.
Okay, so today we're not heading out to the stars. We're going in the opposite direction. Deep, deep into the heart of our own planet. We're going to crack this thing open and really understand the incredible engine that's powering the world right under our feet. All right, let's dive right in. I mean, we spend our entire lives walking around on the Earth's surface, but have you ever really thought about what's going on down below? For centuries, it was a complete mystery, the stuff of myths and legends. So how in the world did we finally crack the case? And that really is the core of the problem, isn't it? I mean, the deepest hole we've ever managed to drill, it barely even scratches the surface. So if we can't physically go down there and take a look, how do we know anything about what's inside? Well, it turns out to be a fantastic scientific detective story. It all came down to two huge clues. First, there was this thing called the density puzzle. See, the rocks we find on the surface are, well, they're relatively light, but when you calculate the Earth's average density, it's way, way heavier. That's a dead giveaway that something incredibly dense must be hiding at the center. And the second clue? This is genius. We basically use earthquakes as a kind of planetary X-ray. By tracking how those seismic waves bend and bounce as they travel through the planet, we can actually map out all the hidden layers inside. Okay, so with those clues in our back pocket, let's actually start our journey down. We're going to peel back the layers one by one, starting with the very ground we're all standing on. So, the very first thing you gotta know is that the crust, well, it's not all the same. You've got the continental crust, that's what makes up the land. And it's pretty thick, but not very dense. But then, the crust under the oceans is way thinner and a whole lot denser. And trust me, this difference isn't just some minor detail. It is absolutely fundamental to how our entire planet works. Okay, let's drop down below the crust. We're now entering the single largest part of our planet, the mantle. Now, a lot of people picture this as a giant sea of lava, but that's not quite right. It's actually a vast layer of incredibly hot, solid rock that, get this, flows like super sick tar over millions and millions of years. And just to give you a real sense of scale here, check out that number, 80%. The mantle makes up a whopping 80% of our planet's total volume. So really, when we talk about the Earth, we're mostly talking about the mantle. That crust we live on, it's just the thinnest, most fragile skin on top of this massive, powerful engine. And finally, we've reached our destination, the core. And this is where things get really wild. You see, the outer core is a swirling ocean of liquid iron and nickel. But right at the very center, the pressure is so incredibly intense that it actually forces that same metal back into a solid, super dense ball. A solid core inside a liquid one. It's a fascinating paradox. So we've got the basic structure down, crust, mantle, and core. But what are these layers actually made of? What's the elemental recipe for building an entire planet from scratch? Well, if you could somehow put the entire Earth into a giant blender, this is pretty much the recipe you'd end up with. Just 4 elements make up almost everything. And look at that, the #1 ingredient, at 35%, is iron. And that right there finally solves our density puzzle. This is where all that heavy stuff ended up. But check this out. Now look what happens when we only look at the crust. The recipe is completely different. All of a sudden, iron is just a tiny little sliver, and the whole chart is dominated by lighter stuff like oxygen and silicon. So what gives? Where did all that heavy iron go? This right here tells the story of the early Earth perfectly. Think about it. When our planet was young and basically a big molten ball, all the heavier elements, yep, like iron, sank right down to the center. That's what formed the core. Meanwhile, all the lighter materials floated to the top and eventually cooled to form the crust. This whole sorting process has a name. It's called differentiation, and it's the simple reason our planet is layered the way it is today. Right, so these layers aren't just sitting there. They're active. The incredible heat escaping from the core creates these huge, slow-moving currents in the mantle. And that movement deep inside the planet, it has massive consequences for us up here on the surface. And here's the crucial idea. The Earth's crust isn't one solid shell. Nope. It's actually broken up into these massive, rigid plates. And these plates are constantly in motion, kind of sliding and gliding over a weaker, softer layer in the upper mantle. This, my friends, is the revolutionary theory of plate tectonics. And I gotta tell you, this wasn't just another theory. For geologists, this was the idea, the one that finally made sense of a million different things they were observing all over the world. It really became the grand, unifying theory for their entire field of study. I mean, think about it this way. Before plate tectonics, geology was kind of a jumble of disconnected facts. But afterward, it suddenly became this cohesive science that could explain how the Earth actually works as a complete system. So why is this one idea so incredibly important? Because it explains the global patterns of the most dramatic events on our planet. You know, why do earthquakes and volcanoes happen where they do? It's not random at all. They happen almost exclusively right along the edges where these massive tectonic plates are grinding against each other, pulling apart, or smashing together. And the wildest part, this is all still happening right now. Entire continents are moving as we speak, at about the same speed your fingernails grow. It's this incredibly slow but totally unstoppable force that has been shaping and reshaping our world for billions of years. Which of course leaves us with one final mind-bending question. What's our world even going to look like in another 100 million years? All right, let's get into it. Today, we're going to crack open one of the greatest geological detective stories of all time. It's a fantastic tale about a radical idea, a puzzle the size of a planet, and a discovery that completely flipped our understanding of the very ground beneath our feet. You know, it all starts with something you've probably noticed yourself, just staring at a world map. Have you ever seen how the big bulge of Africa seems to just nestle perfectly into the curve of South America? Well, that's not just a coincidence. That's clue number one in our mystery. For a long, long time, that little observation was just a curiosity, a weird, that's neat. But it turned out to be the first thread you pull that unravels this massive, planet-sized puzzle that had the world's best scientists just scratching their heads. Yeah, the fit of the continents was really just the tip of the iceberg. The more that scientists looked, the more they found these bizarre, almost ghost-like connections linking lands that were separated by thousands of miles of ocean. And the evidence was just baffling. I mean, how could there be ancient scars from glaciers in the hot deserts of Africa? And get this, the fossils. Mesosaurus was a small freshwater reptile. There is no way it could have swum across the entire Atlantic Ocean. Same story for the land dweller, Lystrosaurus. And the plant Glossopteris? Its seeds were way too heavy to be carried by the wind across such enormous oceans. It just didn't make a lick of sense. So how in the world do you explain all these impossible connections? Well, back in the early 20th century, a German meteorologist, of all people, named Alfred Wegener, came up with a really bold, almost unthinkable explanation. Wegener called his big idea continental drift. He proposed that all the continents we know today were once slammed together into this giant supercontinent he named Pangaea. And suddenly, it all clicked. The fossils matched up, the glacier scars connected, the coastlines fit together, because millions of years ago, they were all one piece. It explained everything. Well, almost everything. As brilliant and, as elegant as Wegener's idea was, it was met with some serious rejection from the scientific community, because his otherwise perfect theory had one giant fatal flaw. This was the question that stumped everybody. Wegener could show that the continents had moved, but he couldn't explain how. I mean, what kind of incredible force would be powerful enough to literally push solid continents through the Earth's crust? To most scientists, it just seemed impossible. So without that missing mechanism, that how, Wegener's theory was pretty much ridiculed and put on a shelf to collect dust. The case of the wandering continents officially went cold for nearly half a century. The case went cold for decades. Then, this unexpected breakthrough came from the darkest, most hidden place on Earth, the deep ocean. New tech that came out of World War II, like sonar, let scientists do something they'd never done before, actually map the huge, secret landscape of the ocean floor. And what they found down there was about to change everything. Snaking its way around the entire globe like the seam on a baseball, they discovered the mid-oceanic ridge. It's the longest mountain chain in the world. And this wasn't just some geographical feature. It turned out to be the very engine that was driving the continents. The answer they found was a process called seafloor spreading. Okay, so think of it like a giant conveyor belt for the entire planet. You've got molten rock constantly welling up from the Earth's mantle right at that ridge, creating brand new ocean floor. As this new floor forms, it shoves the older floor out to the sides, carrying the continents along for the ride. This was it. This was Wegener's missing mechanism, finally found. But science demands proof, right? And the final, undeniable evidence, the absolute smoking gun that proved seafloor spreading was real, was found locked inside the rocks themselves, in the form of a magnetic barcode. This is where a field called paleomagnetism comes in. When volcanic rock cools and solidifies, tiny magnetic minerals inside it line up with the Earth's magnetic field, like trillions of microscopic compass needles. Then they get locked in place, preserving a perfect snapshot of the magnetic field at that very moment in time. Now here's the really wild part. Earth's magnetic field isn't stable. Every few 100,000 years or so, it completely flips. North becomes south and south becomes north. So rocks that form during a normal polarity period, like we have today, point north, while rocks formed during a reversed polarity period actually point south. So as new crust is constantly being made at the mid-ocean ridge, it's recording these magnetic flips over millions and millions of years. The ocean floor essentially becomes this giant, slow-moving magnetic tape, documenting the planet's entire magnetic history and its rocks. And just to give you a sense of the timescale we're talking about, the last time our planet's magnetic field did this whole flip-flop was about 780,000 years ago. We've been in our current normal period, what scientists call a crone, ever since then. So when scientists towed magnetometers across the ocean, this is what they found. It wasn't some random mess. It was a perfect mirror image pattern of magnetic stripes on either side of the ridge. Normal, reversed, normal, reversed. A geological barcode. This was the slam dunk, undeniable proof that the seafloor was spreading from the center, pushing the continents apart. With this discovery, the case was just blown wide open. All the pieces finally fell into place, and it triggered an absolute revolution in our understanding of the Earth. That great mystery that had stumped Wegener, the thing he was ridiculed for, it was finally solved. The continents weren't plowing through the crust itself was moving, and the continents were simply along for the ride. So let's close the case file. Wegener's original clues, the fossils, the glaciers, the puzzle piece fit, they established that a crime had happened. The continents had moved. The mid-oceanic ridge was the scene of the crime. Seafloor spreading was the method, the how, the missing mechanism. And that magnetic barcode on the ocean floor, that was the fingerprint, the undeniable proof that closed the case and gave birth to the modern theory of plate tectonics. And the story isn't over. This process is happening right now as we speak. The Atlantic Ocean is getting wider, the Pacific is shrinking. Which leaves us with one final fascinating question. If this is our world today, what's it going to look like in the deep future? Where are the wandering continents headed next?
All right, let's dig in. Today, we're tackling a question that sounds super simple, but is actually way more specific than you might think. What really is a mineral? Get ready, because the answer involves a very exclusive club with a really strict set of rules.
So, take a look at these three things. What could they possibly have in common? You've got salt that you put on your food, a diamond which is one of the hardest things on Earth, and copper wire that powers our lives. They seem totally different, right? Well, they all share a secret identity. They are all, scientifically speaking, minerals.
So what makes salt a mineral, but something like coal not a mineral? I mean, they both come from the ground, don't they? Well, the first big clue is that salt is inorganic. It doesn't come from living things.
Coal, on the other hand, is basically just ancient squished plants. That makes it organic, and boom, it's kicked out of the mineral club.
Okay, let's try another one. Why is copper in the club, but oil isn't? This rule's a little more obvious. A mineral has to be a solid. Oil, since it's a liquid, well, it just doesn't qualify. So you can see there are some really hard and fast rules here.
And that's what this is all about. It's not just one or two little things. To get the title mineral, a substance has to pass a very strict 5-point test. Think of it like a bouncer at the door of a club, and trust me, there are absolutely no exceptions.
So here they are, the 5 big rules. First, it has to be naturally occurring, so no lab-grown stuff. It has to be inorganic, so sorry, no coal. It must be a solid. It needs a specific chemical composition, like how salt is always NaCl. And number 5, maybe the most important of all, it has to have a crystalline structure.
So, why is that last rule such a big deal? I mean, what even is it? Well, it's so important because this one property, the way its atoms are arranged on the inside, is responsible for some of the wildest differences you see in the natural world.
And to really understand this, let's zoom in on just one element. Carbon. It's an element we all know, right? Is a fundamental building block of life. But in the world of minerals, it has this incredible double life.
And this is where it gets crazy. On the left, you've got graphite, the soft, gray, flaky stuff that's in your pencil. On the right, you have a diamond, the hardest natural thing we know of, perfectly clear. How can these two things be so completely opposite when they are both made of nothing but pure carbon?
The answer is that crystalline structure. See, it's not about the ingredients, it's about the recipe. In graphite, the carbon atoms are lined up in sheets that just slide right past each other, which is why it's so soft. But in a diamond, those same carbon atoms are locked into this super strong, three-dimensional grid. It's like the difference between a neatly built Lego wall and just a pile of loose Lego bricks. Same material, totally different results.
Okay, so we've got the rules down, but with over 4,000 known minerals out there, how do geologists even keep track of them all? Well, they group them into families based on their chemistry, and it's actually a pretty brilliant way to organize this massive library of Earth's materials. And what's really cool is how logical this all is. The name of the group basically tells you the main ingredient. So the oxides, like hematite, that's a metal plus oxygen. The sulfides, like pyrite, fool's gold, that's got sulfur. And then you have the real show-offs, the native elements like gold, that are made of just one thing. But see that group at the top, the silicates? Yeah, remember that one. It's the big one.
So why do these families matter? This isn't just about organizing stuff for a museum. Understanding these groups literally tells us what the ground we're standing on, what the Earth's crust is actually made of.
And here is the recipe for our planet's crust. Just look at this. It's not even close. Oxygen makes up almost half of the crust's weight. Silicon is another quarter. Together, those two elements make up almost 75% of the crust. Everything else, all the iron, aluminum, gold, you name it, is just fighting over the scraps.
So let's connect the dots here. If our planet is just overwhelmingly made of oxygen and silicon, what kind of mineral do you think we're going to find the most of?
Yep, you get silicates. A truly staggering 92% of all the minerals in the Earth's crust belong to that one silicate family. It's the group that combines silicon and oxygen with other elements. It is the undisputed king of the mineral world by a long shot.
And these are the guys you're actually standing on right now. The feldspar family alone, just that one group, makes up about half of the entire Earth's crust. Then you have quartz, micas, and a few others. These aren't rare exotic gems. These are the common, everyday rock-forming minerals that build our entire planet.
But don't think for a second that we found them all. This is a living, breathing science. New minerals are still being discovered, like this one, muralonite. And this quote from the physicist who found it just captures the wonder of it all. It has whiskers that look like scrolls. I mean, how amazing is that? It's a perfect reminder that the Earth definitely still has some secrets up its sleeve.
And that kind of leaves us with one last big thought. We know the rules, we know the big families, and we know what our world is made of. But with new stuff being found every single year, it really makes you wonder what other amazing, incredible new building blocks are still out there, just waiting for us to discover them.
Let's head over to Michigan's Upper Peninsula, to a place that was literally forged by some of the oldest, most powerful volcanic forces on the entire planet, the Keweenaw Peninsula.
It's not just a beautiful spot, it's a geological time capsule, and it's holding some absolutely incredible treasures just waiting to be found.
And that's the big question, right? The rocks here tell a story that's over 1 billion years old, a story of fire, of water, and just immense pressure. What's so amazing is that the clues to understanding this ancient past, well, we can see them in volcanoes that are erupting right now. So take a look. On the left, that's the ancient solid lava of the Keweenaw, and on the right, that's an active lava flow in Iceland today. By studying modern volcanoes just like this one, geologists can basically peer back in time and figure out exactly how the Keweenaw was formed. You see, as these huge fluid flows of lava cooled down, they were setting the stage for something remarkable to happen inside the rock itself. So how in the world do you get from a simple, plain old lava rock to a treasure chest filled with minerals? Well, the magic happens on a really small scale, in a process that transforms empty space into something spectacular. And it all kicks off with gas. It's actually a pretty simple process when you break it down. As all that molten rock started to cool, trapped gases formed bubbles, kind of like when a can of soda goes flat. When the lava finally hardened, these bubbles became permanent empty pockets, creating what we call vesicular rock. But, nature doesn't like to leave empty spaces. Over millions of years, hot, mineral-rich water seeped in and started depositing tiny crystals, filling these pockets up like little geological piggy banks. Okay, so this is the key thing to remember. Think of vesicular rock as potential. It's like an empty apartment building. Amygdaloidal rock, on the other hand, is that potential fulfilled. It's the building where every single apartment is now occupied by a unique mineral tenant. And these filled-in bubbles, they're called amygdules, are exactly where we find the Keweenaw's famous treasures. And wow, what incredible tenants they are. The specific combination of that ancient lava and all that mineral-rich water in the Keweenaw created like the perfect storm for forming some of the world's most unique and valuable deposits. So let's meet the stars of the show. First up is native copper. This is the mineral that really put the whole region on the map. And this isn't some ore that you have to process. We're talking about pure, metallic copper, found here in quantities you just don't see anywhere else on Earth. It literally flowed into the rock, filling up everything from those tiny gas bubbles to much larger cracks and fissures. So what makes it so special? Besides just how much of it there is, native copper is malleable, which means you can hammer it and shape it without it shattering. It's got this jagged, hackly kind of fracture if it does break, and it has a very distinct copper-red streak when you scrape it on a ceramic plate. And that's a key identifier we're going to talk more about in a bit. Now, while that copper was filling the bigger cracks, another amazing treasure was forming in the smaller voids, the Lake Superior agate. These are those absolutely beautiful, banded stones that rockhounds will spend hours and hours searching for along the lakeshore, a real collector's dream. Each and every agate is a perfect little story of this whole process. It used to be a gas bubble, and then it was slowly filled, layer by tiny layer, with a type of quartz called chalcedony. Little trace elements like iron are what create all the different colors and those famous bands, turning every single stone into a unique piece of natural art. All right, now for something much more recent, and a truly surprising discovery. Back in 2017, a whole new kind of rock was found on the shores of Lake Superior, one that holds a secret you can only see in the dark. Meet the euperlite. These are not your average rocks. They have a mineral inside them called sodalite that has this hidden superpower. Under UV light, it glows with this intense, fiery orange. And what's really wild is that these rocks aren't even from the Keweenaw's lava flows. Geologists think they were basically hitchhikers carried all the way down from Canada by massive glaciers, which just adds another cool layer of mystery to the region. Of course, wherever you find rich mineral deposits, a huge economic story is sure to follow. The Keweenaw's geology didn't just create a bunch of pretty rocks. It fueled America's very first great mineral rush. And believe it or not, it continues to be a source of vital resources even today. Just to give you an idea of the modern scale we're talking about, check out the nearby Eagle Mine. It's the only active nickel mine in the entire United States. Its projected yield is a mind-boggling 440 million pounds of nickel, plus nearly 430 million pounds of copper, all from a single location. All that wealth is locked inside specific minerals within a host rock called pyrrhotite. The two big players here are pentlandite, which is the source of the nickel, and chalcopyrite, a major source of copper. The entire goal of modern economic geology is to find these super concentrated ore bodies. Okay, so we've seen what these minerals are and why they're so important. But how do geologists, or, how could you, tell them apart out in the wild? It's not always about having expensive equipment. Sometimes it's just about using a few simple but really powerful tests. Let's take the classic case of fool's gold, also known as pyrite, versus real copper. I mean, they both look metallic. They're both shiny. But the dead giveaway is the streak test. If you scratch pyrite on an unglazed ceramic plate, it leaves a greenish-black streak. Native copper? It leaves that unmistakable copper-red streak. It's as simple as that. You just can't fool a streak plate. Here's another fantastic example. Halite, which is literally just table salt, and calcite can look pretty similar. But halite breaks into perfect little cubes because of its cubic cleavage. Calcite breaks into these slanted rhomb shapes. And if you're ever really unsure, well, halite has a distinct salty taste, and calcite will fizz if you drop a little bit of weak acid on it. These simple properties are a geologist's best friends. From billion-year-old lava flows to glowing stones carried by glaciers, the story of the Keweenaw proves that the ground right under our feet is a history book. It reminds us that incredible secrets are often hidden in plain sight, just waiting for a curious eye and the right question to be asked. So, what history is written in the stones near you?
We walk on it, we build with it, and we call it rock solid. But what if I told you that the very ground beneath our feet has a story? One that starts with incredible fire and pressure deep inside the earth. Well, today we're digging into that fiery origin story. This is the story of igneous rocks.
You know that phrase, rock solid? We use it all the time to mean something is permanent, unchanging. But from a geological point of view, that couldn't be further from the truth. Give it enough time and rocks are in constant motion.
That's because when you think in terms of millions of years, the Earth's crust is an unbelievably dynamic place. I mean, rocks are born, they're weathered down, buried, melted, and then, reborn in a powerful, never-ending cycle.
So here's our game plan for this explainer. We're going to follow that journey, starting with the big picture, the rock cycle. Then we'll see how magma is born, look at its different recipes, see how it's forged in fire, and finally meet the whole igneous family. Let's get right into it.
Okay, Section 1, Earth's ever-changing rocks. So how does our planet actually recycle its most basic building blocks? Well, it all comes down to something called the rock cycle.
All the rocks you'll ever find on Earth fall into one of three main families. You've got sedimentary rocks, which are basically made from little bits and pieces of other rocks. Then there are metamorphic rocks, which are old rocks that have been totally transformed by intense heat and pressure. But our focus today, igneous rocks. Well, they're kind of the ancestors of them all. They're born directly from molten material. They are the planet's original crust.
All right, Section 2, the birth of magma. So, if igneous rocks come from this molten stuff, it begs the question, where does all that molten rock actually come from in the first place? This parent material has a name, magma. It's just hot liquid rock that's found deep inside the Earth. And the only difference between magma and lava is literally just location. If it's underground, we call it magma. The second it erupts onto the surface, we call it lava. Simple as that.
Now hold on, because this is where we have to bust a huge common myth. A lot of us picture the Earth's mantle as this giant ocean of liquid magma, right? Well, it's not. It's definitely hot enough to be liquid, but the incredible pressure from all the rock above it actually squeezes it and forces it to stay in a solid state. Think of it like a really, really hot, dense plastic. So if the mantle is mostly solid, how do we get any magma at all? It turns out you need a special trigger. The first one is decompression. When tectonic plates pull apart, that pressure is suddenly released, and the rock can finally melt. It's kind of like taking the lid off a pressure cooker. Second, just add water. When an oceanic plate gets pushed under a continent, it brings water down with it. That water acts like salt on ice, and it actually lowers the melting point of the rock around it. And third, simple heat transfer. If you have a plume of hot magma rising up, it can just melt the solid rock it comes into contact with, kind of like a hot knife cutting through butter.
Okay, Section 3, a magma's recipe. And just like baking, not all magma is the same. The final rock you get depends completely on its chemical recipe.
So let's break this down into two main flavors. Over on the left, we have felsic magma. The name's a clue.
Fel for feldspar, and sic for silica. It's super high in silica, which makes it really thick and sticky, almost like peanut butter. This is the stuff that forms the light-colored rocks of our continents. On the right, we've got mafic magma. Again, the name tells the story. Ma for magnesium and Fic for ferric iron. It's way lower in silica, so it's dark and runny, more like hot chocolate syrup. And this is the stuff that forms the dense, dark rock of the ocean floor.
All right, so we have our molten magma, we know its chemical recipe. Now comes the really dramatic part, the cooling. This is the process that actually forges the rock and leaves behind the single most important clue for a geologist, its texture.
Now, when a geologist talks about texture, they're not talking about how a rock feels when you touch it. Nope. They're talking about its internal structure, specifically the size of its mineral crystals. Are they big and obvious, easy to see with your naked eye? Or are they tiny, totally microscopic? And the one key factor that determines the crystal size is simply where the cooling happens. If magma cools down really slowly, deep beneath the surface, we call that intrusive. But if it erupts as lava, remember that difference, and cools super quickly on the surface, we call that extrusive.
And here's the direct result of that. Slow cooling gives those crystals a ton of time to grow big and beautiful, creating a coarse-grained texture. The technical term is phaneritic. But fast cooling, well, it basically freezes everything in place instantly, creating a fine-grained texture with microscopic crystals. And we call that aphanitic. So phaneritic, you can see them. Aphanitic, you can't. Okay, Section 5, the igneous family. This is it, the moment we've been waiting for. We have our two main clues, the magma's composition, its recipe, and its cooling history, its texture. Now we can finally put them together and identify our rocks.
And here it is. This simple grid tells us so much. Let's walk through it. If you have that light-colored, sticky felsic magma and it cools slowly underground, that's intrusive, you get granite. But if that exact same felsic magma erupts and cools quickly on the surface, extrusive, you get a rock called rhyolite. Now for the dark stuff. If dark, runny, mafic magma cools slowly underground, you get gabbro. And if it cools quickly on the surface, you get the most common volcanic rock on the entire planet, basalt.
Now, this chart is awesome for putting things in boxes, but these rocks are so much more than just names. They are, quite literally, the foundations of our world. So let's see where you can actually find them.
Let's start with granite. This is our felsic intrusive rock. It forms these enormous bodies of rock deep underground that eventually get pushed up and exposed by erosion. Those magnificent sheer cliffs you see in Yosemite Valley, that's the exposed core of a giant granite formation. You're literally looking at the slow-cooled heart of an ancient mountain range.
Now let's look at its total opposite, basalt. This is our mafic, extrusive rock. When lava erupts from mid-ocean ridges or from massive volcanoes like the ones in Hawaii, it cools down fast and forms basalt. This one rock makes up pretty much the entire floor of our oceans and builds gigantic islands from the seabed up.
So, to wrap this all up, what are the big takeaways from our journey? First, rocks are not static. They are part of a grand, dynamic cycle. Second, magma isn't just hanging out down there. It only forms when solid rock gets a specific trigger to melt. And finally, the two most important clues to any igneous rock story are its composition, is it felsic or mafic, and its texture, which tells you exactly how it cooled down.
So the next time you see a granite countertop, or a field of black lava rock, or even just a cool-looking stone on the ground, remember this. It holds an absolutely epic story of pressure, heat, and transformation. It's a message sent to you from deep within the earth. The only real question is, what story will you discover?
You know, have you ever just picked up a random rock and wondered what kind of story it could tell if it could talk? Well, it turns out some rocks are natural-born storytellers. Today, we are diving deep into the absolutely fascinating world of sedimentary rocks. They're basically the archives of our planet's entire history. So let's kick things off with a number that might just blow your mind. Sedimentary rocks? They only make up about 5% of the Earth's crust by volume. But, and this is the crazy part, they cover a staggering 75% of the land's surface. They are, quite literally, the skin of our planet. They're the part we see, the part we live on every single day. So, okay, why should we care? I mean, it's just rock, right? Wrong. These rocks are so much more than just scenery. They are Earth's diary, holding clues to climates from millions of years ago. They're where we find our fossil fuels. They hold the entire history of life in the fossil record. And they're the source for crucial resources like iron and aluminum. So, to put it simply, understanding these rocks means understanding our planet's past, our present, and yeah, even our future. All right, to really get the full picture, we're going to follow the entire life story of a sedimentary rock. We'll start with what makes them unique, then see how they're born from the rubble of other rocks, follow their incredible journey, watch them transform into solid stone, meet the different rock families, and finally, learn how to read the amazing stories they've recorded for us. First things first, what does it even mean for a rock to be sedimentary? Let's lock in a really clear definition.
At its very core, a sedimentary rock is a recycled rock. It's made from sediment, and that can be anything from tiny weathered bits of older rocks to minerals that were once just dissolved in water. These little pieces gather together, pile up, and then get hardened back into solid rock through a process we call lithification.
You know, every single sedimentary rock begins its life with the destruction of another rock. This first step is called weathering, and it's the process that breaks down solid bedrock into all those smaller, easy-to-move pieces. Now, weathering happens in two main ways. To get the difference, think about a cookie. Mechanical weathering is like taking a hammer and smashing that cookie into crumbs. You get smaller pieces, but it's all still cookie, right? Chemical weathering, on the other hand, is like dropping that cookie in a glass of milk and letting it dissolve. The cookie itself is fundamentally changed. One is a physical beatdown, the other is a chemical transformation. A perfect and really powerful example of this physical force is something called frost wedging. It's so simple, but it's absolutely relentless. Water trickles into a crack in a rock. Then it gets cold, and the water freezes. And as we all know, when water turns to ice, it expands. This expansion acts like a tiny, powerful jack, prying the rock apart from the inside out. Now, one freeze isn't going to do much, but you repeat that cycle thousands and thousands of times, and you can tear entire mountains apart. Okay, so once our rock has been shattered into sediment, it doesn't just hang around. Oh no, it begins a journey, carried away by rivers, wind, and ice. Just imagine these fragments being swept away by a rushing river. This journey is like a natural sorting machine. As the river starts to slow down and lose energy, it drops the heaviest, biggest particles first. We're talking boulders and gravel. But the lighter stuff, the sand and silt, they can travel much, much farther, maybe even all the way out to the ocean. And that sorting process, it gives geologists major clues about the kind of ancient environment where the sediment finally came to rest. So after being carried along and finally dropped off, our loose sediment, whether it's sand on a beach or mud at the bottom of a lake, is now ready for its final incredible transformation, becoming solid rock. The official term for this whole process is lithification. It sounds kind of fancy, but it literally just means stone making. This is the grand finale, where loose piles of sand and mud get turned into the solid, layered rocks we see in places like the Grand Canyon. Lithification basically happens in two key steps. First up is compaction. As more and more layers of sediment pile on top, the sheer weight from above acts like a giant natural press, squeezing all the water out and forcing the grains closer and closer together. Then comes cementation. You can think of this as nature's superglue. Minerals that were dissolved in the water start to crystallize in the tiny spaces between the grains, locking them all together into one solid mass. So now that we know how they're made, let's meet the family. See, sedimentary rocks aren't all the same. They're actually classified based on their own unique origin story, what they're made of and how they were formed. It really boils down to two main branches on the family tree. You've got your detrital rocks, which are made from those solid bits and pieces, the clasts of weathered rock we've been talking about. And then you have chemical rocks, which form from minerals that were once dissolved in water. The key to telling them apart is actually pretty simple. For detrital rocks, you just look at the size of the particles. For chemical rocks, you look at what they're made of, their mineral makeup. So for these detrital rocks, it's all about size. If the cemented particles are big, like gravel, you get a rock called conglomerate if the pieces are all rounded off from a long journey, or a breccia if they're sharp and angular, which tells you they didn't travel very far. If the particles are sand-sized, you get the rock we all know and love, sandstone. And if the grains are super, super fine, like mud, you get shale, which, believe it or not, is actually the most common sedimentary rock on the planet. Now, the chemical rock family is incredibly diverse. The most common one is limestone, which is often formed from the calcite shells of marine creatures like coral.
evaporates, like rock salt, are exactly what they sound like. They're the minerals left behind when a body of water evaporates. Chert is made of silica from the microscopic shells of plankton. And then you have coal, which is super unique because it's an organic rock, formed not from minerals, but from tons of compressed ancient plants. Okay, so we've followed the journey, we've made our rock. Now for the payoff. This is the really exciting part. Learning how to read the stories these rocks have been holding on to for millions and millions of years. The biggest clue, the dead giveaway, comes from their layers, which are also known as strata. These distinct layers are their #1 feature. Each layer represents a different period of time, like a snapshot. Honestly, you can think of them as the pages in Earth's giant history book, with the oldest pages way down at the bottom and the newest ones right up at the top. And what do you find tucked away within these pages? Fossils. They're like the illustrations in our history book. Fossils are, of course, direct proof of prehistoric life, but they also tell us so much about the environment at that time. Find a fish fossil? You know that area was underwater. They also act like little time markers, allowing geologists to match up rock layers across huge distances, piecing together a truly global history of our planet. And all of this brings us to a final, pretty mind-bending question. Millions of years from now, future geologists might be studying the sedimentary layers being formed right now, today. And they'll find things like plastics, bits of concrete, and chemical signatures that are totally unique to our time. So what story will the sediments of our era, the Anthropocene, tell about us? It's a powerful thought, and it's a reminder that we are all, right now, actively writing the next page in Earth's incredible stone diary.
All right, let's talk about one of the most fascinating types of rocks out there, metamorphic rocks. Now, these aren't just any old stones. They've got a wild story to tell, a history of incredible transformation that's literally written right into their structure. So let's dig in and read that story.
You've probably seen this before, right? You're out on a hike, or you see a picture of a mountainside, and there's this rock that looks completely, well, bent out of shape. It's got these swirling, wavy bands, and it looks like it's been totally twisted. It looks kind of chaotic, but believe me, that chaos is actually a clue to an absolutely epic story of change.
So, what's going on here? The answer is a process called metamorphism. The word literally means to change form, and that's exactly what happens. You take any rock, igneous, sedimentary, even another metamorphic one, and you subject it to insane levels of heat and pressure deep inside the earth. Now here's the crucial part. It changes while staying completely solid. The second it melts, poof, it's magma, and that's a whole different story that leads to igneous rocks.
Okay, so how does a rock just change form without melting? Well, the best way to think about it is like a recipe. Seriously, just like baking, you need the right ingredients and you need the right conditions in the oven. For metamorphic rocks, these ingredients are what we call the agents of change.
So, what's in this geological recipe? There are 3 main things. First, and this is the big one, is heat. You can get that from being near a body of magma or just from being buried miles deep in the Earth's crust. Second, you've got pressure or stress. This is the squeezing, the compressing force. And finally, you have these chemically active fluids, which are mostly just super hot water, that act like a catalyst to help speed the whole process up.
And if we have a recipe, we need a kitchen, right? In geology, there are basically 2 main kinds. First is what we call contact metamorphism. Think of this as putting a rock right next to the heating element in an oven. It's all about intense heat from nearby magma. It gets baked. Then there's regional metamorphism. This happens over huge areas, usually when mountains are being built. This is the kitchen where rocks get both baked and squeezed by immense tectonic forces. To really see how this works, I think the best way is to follow the journey of a single rock as it gets put under more and more intense conditions. This is where the story gets really, really cool.
So every single metamorphic rock has to start as something else, right? Geologists have a great name for this original rock, the protolith, which basically just means parent rock. For our story, our parent rock is going to be good old shale. Yep, it's a super common sedimentary rock that's essentially just a bunch of hardened mud and clay.
Now, imagine our simple shale getting buried deeper and deeper. With a bit of heat and pressure, it first gets squeezed into slate. The clay minerals align perfectly, which is why it splits into those nice flat sheets. Now, let's turn up the heat and pressure a little more. Those minerals start to grow, and the rock gets a kind of silky, glossy sheen. Bam, you get phyllite. Crank that geologic dial even higher, and those shiny minerals become big enough to see with the naked eye. Now we've got schist.
And then, for the grand finale, under the most intense conditions, the dark and light minerals actually separate into distinct bands. You get the classic, wavy-looking gneiss. You can literally see the journey from a dull mudstone to this complex, beautiful rock.
Okay, so that whole story, from shale all the way to gneiss, was all about the squeeze. That directional pressure is what created all those layers. But what happens if you just bake a rock? What if you take away that intense, directional squishing?
Well, that brings us to a whole different family of rocks, the non-foliated ones. No layers, no bands. Why? Because they weren't squeezed in one direction. They were mostly just cooked. Instead of minerals lining up in layers, their existing mineral grains just kind of grow larger and fuse together into a strong, interlocking texture.
Let's look at a classic before and after. We start with our parent rock, or protolith, which is limestone. You know, that sedimentary rock made from the calcite shells of ancient marine life.
You take that limestone, you bake it with intense heat, and what do you get? The gorgeous crystalline rock we all know and love, marble. All those tiny calcite crystals in the limestone have just recrystallized into larger, interlocking crystals. Same stuff, totally new texture.
Here's another great one for you. This time, we start with sandstone. As the name suggests, it's just a bunch of tiny quartz sand grains that have been cemented together over time.
Now, you cook that sandstone under intense heat, and those little sand grains literally weld themselves together. You end up with this incredibly tough, durable rock called quartzite. It is so solid that if you try to break it, the rock will fracture right through the original quartz grains, not around them. That's how strong that new bond is.
Okay, so let's put it all together in a quick cheat sheet. On one side, you have your foliated rocks, like gneiss. Just think layers and squeezing. On the other side, you've got non-foliated rocks, like marble. Think no layers and baking. Squeezed versus baked. It really is a great way to start classifying these amazing rocks.
But here's where it gets mind-blowing. These rocks aren't just pretty to look at. They're time capsules. They're actual historical documents that tell geologists exactly what the conditions were like deep inside the Earth millions, even billions of years ago.
So, how do they read this history book? They look for special clues called index minerals. You can think of these as tiny geological thermometers and pressure gauges. These are special minerals that can only form and stay stable within a very specific, narrow window of temperature and pressure.
So, when a geologist cracks open a rock and finds a mineral like a garnet or kyanite or sillimanite, it's like finding a secret message. Each mineral tells them, hey, when I was formed, it was this hot and the pressure was this intense. It's a secret code that allows them to map out the entire history of ancient mountain ranges. It's absolutely incredible stuff.
So the next time you see one of those twisted, banded rocks on a mountainside, or even just a marble countertop in a kitchen, stop for a second. You're not just looking at a piece of stone. You're looking at a survivor. You're looking at an ancient story of fire, pressure, and incredible transformation. And it really makes you wonder, doesn't it? What kind of stories are the rocks right under your own feet just waiting to tell?
Welcome to The Explainer. You know, have you ever just stood at the bottom of a huge mountain, looked all the way up, and thought, how in the world did that get there? How does solid rock pile up for miles into the sky? Well, today we're going to dig into the very architecture of our planet to find out. So let's kick things off with a really basic question. I mean, think about it. The Earth is just this giant sphere of rock, right? So why isn't it perfectly smooth, like a cue ball? What is it that carves out these incredibly deep valleys and pushes up the towering mountains that make our world so interesting? You know, the answer actually starts with something you can't even see. It's a force that's happening all the time, right beneath our feet. Geologists have a simple name for it: stress. And this invisible force is the engine that drives pretty much all major change on our planet. So what is stress exactly? Well, to put it simply, it's just the amount of force being pushed or pulled on a certain area of rock. You can almost picture the planet constantly squeezing, stretching, and twisting its own skin. And what's super interesting here is that this stress isn't just one thing. It comes in three main flavors. First, you've got compressional stress. That's a squeezing force. Then there's tensional stress, which, you guessed it, pulls things apart. And finally, you have shear stress, where huge blocks of rock just slide right past each other. And, as you can probably imagine, each one of these creates a totally different result. Okay, so what happens when you put all this stress on a massive piece of rock? Well, once you push it past what's called its elastic limit,
That's the point where it can't just snap back to its original shape. It's really only got two choices. It can either break, which geologists call brittle deformation, or it can bend, which is called ductile deformation. And the comparison here is just perfect. Brittle deformation is just like snapping a cold candy bar. It's rigid and just shatters. That's what happens in the cooler upper layers of the Earth's crust. Ductile deformation, though, is way more like bending a warm piece of taffy. It gets all soft and gooey and it flows, and that's what happens way down in the hotter, deeper parts of the crust.
And this, right here, this is the main idea for today. These two incredibly simple actions, bending and breaking, are literally the building blocks for every major feature you see on the surface of the Earth, from a tiny little crack in a rock to the absolutely massive Himalayan mountains.
All right, so let's zoom in on that first option, bending. What kind of amazing things get created when rocks choose to go with the flow, when they undergo that ductile deformation and literally bend under unbelievable pressure? Well, you get these absolutely beautiful structures called folds. They're basically giant waves that have been frozen in solid rock. They're caused by that squeezing compressional stress, which shortens the crust from side to side. And just like when you push a rug from both ends, it has nowhere to go but up, so the crust gets thicker. Now, the two most common types you'll hear about are anticlines and synclines, and there's a super easy way to remember this. An anticline looks like an arch, like the letter A. A syncline sinks down, forming a U shape, like a smile. And for geologists, one of the key differences is that in an anticline, the oldest rocks get pushed up to the center, while in a syncline, you'll find the youngest rocks right there in the middle. Okay, so that's what happens when rocks decide to bend. But what about that other option, the more sudden, more dramatic one? Let's dive into what happens when rocks just can't take the pressure anymore, and they give in to brittle deformation and just break. When rocks break and there's movement along that crack, we call it a fault. And the key word there is movement. A simple crack in a rock is just a fracture. But the second one side starts to shift relative to the other, boom, you've officially got a fault. Now, to really get a handle on the different kinds of faults, we need to know two quick terms. Just picture you're a miner standing in a tunnel that's been dug right along the fault. The big block of rock hanging over your head, that's the hanging wall. And the rock that's down below your feet, that's the footwall. See? Simple as that. Okay, so this is the crucial part. It's all about how that hanging wall moves. When the crust is being stretched and pulled apart by tensional stress, the hanging wall drops down. That's a normal fault. But when the crust is being squeezed together by compressional stress, the hanging wall gets pushed up and over the footwall, and that's a reverse fault. But wait, what about that third type of stress, shear stress? Well, that creates our third major type of fault, the strike-slip fault. And here, the movement isn't up or down at all. It's totally horizontal. The two giant blocks of rock are just grinding sideways past one another. And of course, the most famous example of this on the planet is the San Andreas Fault out in California. It's a massive strike-slip fault. They call it a right lateral fault because if you were to stand on one side of it and look across to the other, the ground on the other side would look like it's moving to your right. So let's recap. We've got bending, which makes folds, and we've got breaking, which makes faults. Now for the really big question. How did these two things work together to build something as mind-bogglingly huge as a mountain range? Well, the fancy scientific name for mountain building is orogenesis. It's basically the sum total of all these geological processes, and it's all driven by the slow, constant, unstoppable movement of our planet's tectonic plates. Almost all of the world's major mountain ranges are formed where these plates are crashing into each other in the slowest motion collision you can possibly imagine. At these collision zones, geologists have figured out there are basically three main recipes for cooking up some mountains. First, you can have two oceanic plates collide, which creates volcanic island arcs, like Japan. Second, you can have an oceanic plate dive underneath a continent, which builds a coastal range, like the Andes. And then there's the third, most powerful recipe of all, two continents smashing into each other head-on. And when that happens, all that rock has nowhere to go, but straight up. And this brings us to the ultimate showcase. That continental collision between the Indian and Eurasian plates is what's called an alpine-type orogeny. And what did it create? Oh, just the Himalayas, the highest mountain range on the face of the Earth, with the absolutely incredible peak of Mount Everest at its summit. So let's put the whole story together one last time. It all begins with that invisible force we call stress. In response, rocks either bend and create folds, or they break and create faults. Then, over millions upon millions of years, all those folds and faults just keep stacking up, squishing and thickening the Earth's crust until they form the incredible, majestic mountain ranges we see today.
And that leaves us with a pretty wild final thought. This whole process of orogenesis, it's not over. It's not ancient history. The Indian plate is still pushing into Asia right now. The plates are always moving. The very same forces that built the mountains of the past are silently working away right now, shaping the world of tomorrow. So I'll leave you with this to think about. What will the mountains of the future look like?
All right, let's just jump right in. I want you to imagine trying to read the most incredible story ever written. It's a story that's billions of years old, with chapters of fire, ice, and life itself. But here's the catch. The book is the Earth. Its pages are layers of rock, and, well, there are no words. So today, we're going to become geological detectives. We're going to figure out how to read this amazing story. And that's the big question, right? How in the world do you read a story that's billions of years old with no words? I mean, it seems completely impossible. But here's the cool part. The rocks, they have their own language, their own grammar. And we're about to learn how to speak it. Okay, so with any huge mystery, you need a key, right? You need that one fundamental idea that just unlocks everything else. For geology, that key turned out to be a total, radical shift in how we think about time itself. For a long, long time, the main idea was something called catastrophism. The thinking was, that the Earth was shaped by these sudden, massive, violent events, the kind of things that happened over just a few thousand years. But then, in the late 1700s, a geologist named James Hutton came along with a completely different idea, uniformitarianism. He looked around and said, hey, what if the slow, steady processes we see happening right now, like rivers carving out canyons, have been going on for an unbelievably long time? And this quote from Hutton, it just sums it all up perfectly. The present is the key to the past. I mean, what a profound statement. It's the bedrock, literally, of modern geology. What it means is that the laws of physics and chemistry we see today, they've always been in effect. So by studying what's happening now, we can figure out what happened millions, even billions of years ago. This was a Rosetta Stone. This changed everything. All right, so now that we have this amazing key, this foundational principle, geologists could start building a toolkit, a set of rules, really, for reading the rock layers in the right order. So let's open up that toolkit and see what's inside. First up, and this is the big one, the most fundamental tool of all, the principle of superposition. It was actually figured out way back in 1669 by Nicholas Steno, and it's just incredibly logical. Think about it. When sediments, like sand or mud, settle out of water, they form layers, right? The very first layer to form is going to be at the bottom, and then the next layers just pile up on top of it. It's kind of like a laundry basket, seriously. The clothes you wore on Monday, they're at the very bottom. Tuesdays are on top of that, and by Friday, those clothes are right at the top. Simple, right? Unless you go and shake the whole thing up, you know exactly what order you wore them in. Well, rocks work the exact same way. Oldest at the bottom, youngest at the top. Okay, next tool in the kit is the principle of original horizontality. It sounds complicated, but it's not. Basically, gravity is going to do its thing. It pulls sediment down, so it settles in flat, horizontal layers. So what does that mean for us? Well, if you're out hiking and you see rock layers that are tilted or folded into these crazy wavy patterns, you know for a fact that some huge event, like an earthquake or mountains being built, had to happen after those layers were laid down flat. Now this is a real game changer for figuring out the timeline of events. It's called the principle of cross-cutting relationships. All it says is that if some geologic feature, like a fault line, cuts across a bunch of rock layers, that feature has to be younger than the rocks it cuts through. The logic is just so simple and elegant. Think about a crack in your phone screen. You can't crack a screen that doesn't exist yet, right? The screen had to be there first, then the crack happened. It's the exact same idea with rocks. Those layers had to be there, all settled and solid, before a fault could come along and crack through them. It's such a powerful way to put events in the right order. And for our last basic tool, we have the principle of inclusions. So if you're looking at a rock and you see little chunks or fragments of a different rock type stuck inside it,
Well, those fragments, we call them inclusions, they had to exist first. They're older. My favorite analogy for this is chocolate chips in a cookie. You gotta have the chocolate chips already made before you can mix them into the cookie dough, right? Same thing. Okay, so now we've got our basic toolkit. We're ready to start reading the story. But there's a catch. The Earth's history book isn't always complete. Sometimes entire pages or even whole chapters are just ripped out. In geology, we call these missing pages unconformities. So what exactly is an unconformity? Well, it's a surface in the rock record that represents a huge gap in time. It's a boundary where much, much younger rocks are sitting directly on top of much, much older rocks. And that gap tells us a story of its own. A story where maybe for millions of years, no new rock was being made, or old rock layers were being completely eroded away, just erased from history, before the story started up again. And there are three main types to look for. First up, you've got the angular unconformity. This one is super dramatic. You see these older layers that are all tilted, and then sitting right on top of them are these perfectly flat younger layers. It just screams that a huge event happened in between. Then there's the disconformity. Now this one's a bit sneaky. The layers are parallel, so it just looks like a normal boundary, but it could represent millions of years of lost time. And finally, the nonconformity. This is where you see layered sedimentary rock sitting on top of a completely different type of rock, like an old eroded granite. Each one tells a unique story of uplift, erosion, and time. So, we're getting pretty good at reading the story in one spot, right? Even with the missing pages. But how do we know if a chapter we're reading in North America is the same chapter as one in Europe? How do we connect or correlate the story across huge distances? Well, the answer, it turns out, was buried in the rocks all along. Fossils. This brings us to the principle of faunal succession, a brilliant discovery by a guy named William Smith. What he figured out was that life on Earth hasn't been random. It's changed and evolved over time in a very specific, predictable order. So different rock layers contain their own unique collections of fossils. This is huge. It means that any specific period in Earth's history can be recognized by the fossils in it, no matter where on the planet you are. And some fossils are way more useful than others. We call these index fossils, and they are basically the geologist's ultimate cheat sheet for telling time. To be a really good index fossil, an organism had to check a few boxes. It needed to have lived all over the world, but, and this is key, only for a very short period of geologic time. Imagine a species that was everywhere for, say, 1 million years, and then poof, it was gone. If you find that fossil in a rock in Utah, and then you find it in a rock in China, you can be absolutely positive that both of those rock layers were formed during that same million-year window. It's how we sync up the entire planet's story. Okay, so now it's your turn. You've got the toolkit. You have the principles. When you look at a crazy, complex rock formation like this one, it's not just a jumble of rocks anymore, is it? It's a story. It's a sequence of events waiting to be read. So, I'm going to challenge you. Take a look at this. Can you figure it out? What happened first? What happened last? You can do this. And that's really the magic of it all, isn't it? The story of our planet is this massive, epic puzzle, but it's not unsolvable. With these principles, superposition, cross-cutting relationships, and the fossil record, we can actually piece together its incredible history, one single layer at a time. Which leaves us with one last, kind of mind-blowing thought. If the present is the key to the past, that also means that right now, as we speak, we are creating the rock layers of the future. So what story are we writing? Millions of years from now, what will our layers tell the geologists of the future? What will our fossil record, our cities, our plastics, all of our stuff say about who we were?
Have you ever just stood at the edge of a canyon or picked up a cool-looking rock and thought, how do we actually know how old this stuff is? I mean, not just a guess, but a real solid number. Well, today we're going to crack open the planet's geological diary and learn how to read it. We're talking about the incredible science of radiometric dating.
It really all comes down to this one huge question. You hear that number all the time, right? 4.5 billion years. But it wasn't just pulled out of a hat. Getting to that number is one of the greatest scientific detective stories ever told. And believe me, it started with a few really interesting wrong turns.
So before we could even get close to the right answer, scientists first had to wrap their heads around the sheer scale of the puzzle they were facing. And yeah, those early attempts, while pretty clever, were, well, they were way off.
For example, one idea was to measure how salty the oceans are, and then try to calculate backwards to figure out how long it took for all that salt to wash into them. It's a creative thought for sure, but it just missed way too many variables and gave an age that was way, way too young. It was obvious they needed a totally different kind of clock.
And then, bam, the whole game changed. The discovery that some atoms aren't stable, that they can just spontaneously break down, radioactivity, it completely blew the doors off how we think about time. It turned out that nature had hidden the perfect clock right inside the elements that make up our world.
Okay, so what is this hidden clock? It's not made of gears and springs. It's atomic. And to really get it, we need to take a quick peek at the building blocks of matter itself.
All right, think of an element, like carbon. Now, most carbon atoms are the same, but every so often, you get one with a few extra neutrons, which makes it a little heavier. These different versions of an element are called isotopes. And here's the kicker. Some of them are unstable, they're radioactive. And that instability, that predictable need to change, is the engine that makes our clock tick.
This is the secret right here. An unstable parent isotope will, over time, decay. It changes into a completely new, stable daughter isotope. And the most important part? This decay happens at a rate that is perfectly, absolutely predictable. It's like a single, reliable tick of a cosmic clock that has never been wrong. Now, if that decay is the tick, then how do we actually read the time? Well, we use an amazing concept called half-life, and this is where the genius of it all really comes together. So, for any given radioactive isotope, its half-life is a constant. It's a set amount of time. Could be thousands of years, could be billions, but it never ever speeds up or slows down. It's truly one of the most reliable timers in the entire universe.
Let's just walk through it. When a rock first cools and forms, let's say it's got 100% of our parent isotope. Okay, fast forward one half-life. Now the ratio is a perfect 50-50. Wait another half-life, now it's 25% parent and 75% daughter. You see the pattern? By measuring the ratio of parent to daughter atoms in a rock today, we can figure out exactly how many half-lives have gone by since that rock was born.
So if we crack open a rock and we find this perfect 50-50 split, we know, without a doubt, that exactly one half-life has passed.
And if we find this ratio, 25-75, we know it's been 2 half-lives. It's like counting tree rings, but on an atomic scale, to measure time in millions or even billions of years. It's incredible.
Okay, so that's the theory, which is really cool. But how does this work out in the field? How does a geologist actually take this idea and apply it to a real-life rock?
First things first, you gotta pick the right tool for the job. You've probably heard of carbon-14 dating. Its half-life is pretty short, just over 5,000 years. That makes it perfect for dating things like old bones or wood. But to date the Earth itself, you need a clock with a really, really long tick, something like uranium-238. Its half-life is 4.5 billion years, the perfect clock for measuring deep geologic time.
But for this to work, the conditions have to be just right. Geologists need what's called a closed system, basically a sample where nothing has leaked in or out. Igneous rocks, the ones formed from cooled magma, are perfect for this because their crystals lock everything in place. Then they use an amazing machine called a mass spectrometer to literally count the individual parent and daughter atoms and get that all-important ratio.
So after all this painstaking work, what's the big payoff? It's huge. It's nothing less than the ability to write the official biography of our planet, a geologic timescale with real, absolute dates.
Let this number just sink in for a second. 88%. Because of radiometric dating, we now know that a mind-blogging 88% of our planet's entire history happened before the first complex animals ever showed up. This immense stretch of time is called the Precambrian.
And this chart just puts it all into perspective. Look at that. The entire history of complex life, from the first fish, through the dinosaurs, all the way to us, it's all packed into that tiny little bar on the right. Everything else, the first 4 billion years of our planet's story, is that giant bar. Without radiometric dating, that whole vast history was just a complete mystery. And this is the calendar it let us build. We can now lay out the great chapters of Earth's story, the fiery beginnings in the Precambrian, the explosion of strange life in the Paleozoic, the age of dinosaurs in the Mesozoic, and finally, our own time, the age of mammals in the Cenozoic. Every single date on this timeline is thanks to those tiny atomic clocks ticking away silently inside the rocks. You know, when you really learn to read our planet's deep past, It gives you a totally new perspective on our own, very fleeting moment in this timeline. We've mapped out 4.5 billion years. Kind of makes you wonder, what story will the rocks of today end up telling about us?
You know when you see a massive carved-out valley or maybe a string of beautiful, sparkling lakes, and you just have to wonder, what could have possibly shaped that? Well, the architect wasn't a person, and it wasn't some single cataclysmic event. Nope, it was an impossibly slow, unbelievably powerful force of nature. And today, we're going to dig into exactly what it is and how it works.
So what are we talking about here? What has the sheer strength to grind down entire mountain ranges, carry boulders the size of a house for miles, and totally rearrange the landscape, but is born from something as delicate as a single snowflake?
You got it. Glaciers, these colossal rivers of ice are, without a doubt, some of the most powerful agents of change on our planet. Their story? Well, it's written directly into the land we walk on every single day.
Okay, so to really get a handle on their power, we first have to understand what they are. What exactly makes a huge chunk of ice a glacier?
It really comes down to a few key things. First, it has to form on land. Then, it's got to come from snow that's been piled up and squeezed for years and years. But here's the real kicker, the thing that makes it a glacier. It has to be moving. It flows under its own incredible weight. A glacier isn't just sitting there. It's a river of ice, always in motion. And just how important are they? Well, get this. Glaciers hold about 75% of all the world's freshwater. I mean, think about that. They are, quite literally, our planet's most critical water towers. Absolutely staggering.
So how do you get from a delicate little snowflake to a planet-sculpting giant? It's a pretty amazing transformation that can take decades or even centuries to happen.
So it all starts with snow. Snow that doesn't melt in the summer. Year after year, new layers pile on, and all that weight starts squeezing the air out of the old layers below. This packs the snow into this dense, granular stage called firn. Now, you add even more pressure and more time, and that firn recrystallizes into this incredibly dense, often blue-tinted ice that makes up the glacier.
You can kind of think about a glacier's health like a budget. Way up high in the mountains, it's gaining snow and ice. That's its income, the zone of accumulation. But down at the lower end, it's losing ice from melting and huge chunks breaking off. That's its expenses, the zone of ablation. And the balance between that gain and loss, that's everything.
And this constant tug-of-war between gaining ice and losing ice is exactly what drives a glacier's most defining feature. Its slow, powerful, unstoppable movement.
So how does a solid block of ice flow like a river? It happens in two main ways. First, deep down inside, the insane pressure actually makes the ice crystals deform and flow, kind of like super thick honey. That's called plastic flow. Second, meltwater can get to the bottom and act like a lubricant, letting the whole glacier slide across the bedrock. We call that basal slip. And all that stretching and moving puts a ton of stress on the brittle ice at the surface, which is what cracks open to form those massive, terrifying crevasses.
And this brings us back to that really simple and honestly perfect way to think about a glacier's health. It really is like a bank account. Accumulation is your deposit, and ablation is your withdrawal. The balance between those two tells you the whole story.
And the results of this budget are pretty straightforward. If you've got more deposits than withdrawals, the glacier advances, it gets bigger. If the withdrawals are winning, the glacier retreats. Now here's a super important point. Even when a glacier is retreating, the ice is still flowing downhill. It's just melting at the front faster than it can move forward. And of course, if the budget is balanced, the glacier stays more or less stable.
Okay, so this constant movement is what gives glaciers their incredible power. As they flow, they aren't just passing over the land. They are actively, dramatically, and permanently reshaping it. So glaciers are basically master sculptors, and they have two main tools. The first is called plucking. Meltwater seeps into cracks in the rock below, it freezes, and it basically glues the rock to the bottom of the glacier. Then, as the glacier moves, it just rips these huge blocks of rock right out. The second tool is abrasion. The glacier uses all those rocks it just plucked as a giant piece of sandpaper, grinding and polishing the bedrock as it slides over everything.
And the results of all this work? Well, they're some of the most spectacular landscapes on Earth. Glaciers take these sharp V-shaped river valleys and just carve them out into these broad, classic U-shaped valleys. Way up high, they scoop out these incredible bowl-shaped basins called cirques.
And where these massive valleys meet the ocean, they form those breathtaking, steep-walled fjords we all love to see pictures of.
But the story doesn't end when the ice finally melts and retreats. A glacier's departure leaves behind a totally new landscape, a whole legacy written in rock, dirt, and water.
So all that stuff a glacier carries, rocks, boulders, sand, dirt, it has to go somewhere, right? Geologists call all of it glacial drift, and it comes in two main flavors. You've got till, which is the jumbled, unsorted mess of stuff dropped directly by the ice, and then you have stratified drift, which is all the sediment that gets neatly sorted and laid down by the glacier's meltwater rivers.
And you've probably seen these features a million times without even realizing what they were. Moraines are these long ridges of till that basically act like conveyor belt drop-offs, marking how far a glacier reached. Drumlins are these smooth, teardrop-shaped hills that actually point in the direction the ice was flowing. And tons of small lakes, called kettle lakes, formed from giant chunks of ice that broke off, got buried in sediment, and then just melted away, leaving a hole that filled with water.
It's really important to remember that this whole sculpting process wasn't a one-time thing. For the last 2 million years, Earth has been cycling through massive ice ages. I mean, at the peak of the last one, just 18,000 years ago, which is like a blink of an eye in geologic time, colossal ice sheets covered huge parts of North America and Europe. The warmer world we're living in right now, it's just a brief interglacial period in a much, much larger cycle.
So from a single snowflake to a force that can literally move mountains, glaciers are just a fundamental part of our planet's story. They're archives of our past climate and the architects of the world we see today. And that leads us to a final, really critical question. As these ancient, powerful giants shrink at a faster and faster rate, what new story is their absence starting to write about our planet's future?
Have you ever stopped to think about what's really going on when you fill up your car or flip on a light switch? You're actually tapping into a story that started millions and millions of years ago. Today, we're going to take a journey deep into the Earth's past to see exactly how ancient life became the fuel that literally powers our world. So, let's dig in.
I mean, that's a pretty wild thought, isn't it? The energy that's getting you down the highway today is literally ancient sunlight. Sunshine that was captured by plants and tiny organisms way back in the age of the dinosaurs. So how in the world did that sunlight get bottled up underground, just waiting for us? Well, that's the exact story we're going to unpack right now.
You know, whether we're talking about solid coal, liquid oil, or natural gas, it turns out they all come from the same basic recipe. And in this geological kitchen, nature is the head chef. Now, it's a super slow cooking process, we're talking millions of years here, but the ingredients themselves, they're actually pretty simple.
So, what's in this recipe? Okay, first you start with a whole lot of organic matter. We're talking the remains of ancient life. Then, and this is crucial, you've got to bury it fast before it has a chance to rot away. Next, you'll apply a ton of heat and pressure from all the rock piling up on top. And the final, absolutely essential ingredient? Time. Lots and lots of time. Millions of years of it. But here's where it gets interesting. While the basic recipe is the same, the specific starting ingredient changes everything. It determines which path we go down. On one side, you've got the thick, heavy vegetation from ancient swamps, and that's what leads us to coal. But on the other side, you have all the microscopic life from ancient oceans, and that's what gives us oil and natural gas.
All right, let's start our journey on land and follow the story of coal. I mean, this is the stuff that powered the entire Industrial Revolution, and its story starts in a very specific, very wet environment. The key thing to get here is the environment. See, in a normal forest, if a tree falls, it just rots, and its carbon goes back into the air. But a swamp? That's different. The stagnant, oxygen-starved water basically acts like a preservative. It pickles the plant matter, stopping it from breaking down and allowing these really thick layers to just build up over time.
So as all this stuff gets buried deeper and deeper over millions of years, the heat and pressure really start to cook it. It begins as peat, which is basically just compressed bog plants. With more pressure, water gets squeezed out, and it compacts into lignite, which is a soft, brownish coal. Go even deeper, and it becomes the high-energy bituminous coal, the real workhorse of the industrial age. And finally, with maximum heat and pressure, it turns into shiny, hard anthracite, the highest grade of coal you can get.
And what's so cool about this chart is you can literally see that transformation pay off. As you go up the ranks from lignite to anthracite, what you're really doing is squeezing out more water and other junk, which concentrates the carbon. And it's simple. The more concentrated the carbon, the more energy you get when you burn it. Okay, time to leave the swamps behind us and dive deep into the oceans. The story of oil and gas is just as ancient, but its beginnings are microscopic. It all starts with the zillions of tiny organisms that filled the prehistoric seas.
So instead of huge ferns and trees, the main ingredient here is this constant, slow-motion rain of dead plankton and algae drifting down to the seafloor. And just like with coal, the secret sauce is getting it buried quickly in mud that doesn't have a lot of oxygen, locking away all that valuable carbon.
Now this organic-rich mud, once it hardens into a rock like shale, is what geologists call the source rock, and you should absolutely think of it as the geological kitchen. This is where all the action happens. It's where that incredible heat and pressure slowly cook the ancient organic gunk, transforming it into the raw hydrocarbons we know as oil and gas.
But here's the thing. Once the oil and gas are cooked, they don't just hang out in the kitchen. They're lighter than the water in the rocks around them, so they start to float up. They keep moving until they hit a reservoir rock, something porous like sandstone that acts like a giant rocky sponge, soaking up and holding all that oil and gas in its tiny little spaces.
Of course, a sponge or a container isn't much good without a lid, right? That's where the cap rock comes in. This is a layer of rock that's totally impermeable. Think dense shale or even a layer of salt that the oil and gas just can't get through. It acts like a perfect seal, trapping the fuel in that reservoir rock below it. That's what creates the concentrated deposits we're looking for.
And that whole cooking process? It's incredibly picky. Geologists call the perfect temperature range the oil window, which is usually somewhere between about 65 and 150 degrees Celsius. If the source rock is any cooler than that, the organic stuff never cooks. But if it gets too hot, the complex oil molecules literally crack apart and break down into the much simpler, shorter chains of natural gas. It has to be just right.
So, let's review. You need the source rock kitchen, the reservoir container, and the cap rock seal. But you also need them all arranged in a very specific way. Nature has to create what's called a geological trap, a special structure that funnels all that migrating oil and gas into one spot.
And these traps come in all sorts of shapes. An anticline is basically a big upward fold, like an arch in the rock layers. The oil and gas flow to the very top and get stuck. A fault trap is where the rock layers crack and shift, pushing a spongy reservoir rock up against a solid, impermeable one, creating a dead end. In some areas, you even have huge blobs of salt that push up from below, creating traps all around them. It's this incredibly complex geological puzzle that prospectors are always trying to solve.
For more than 100 years, finding those traps was the whole game. But as our technology has gotten better and better, so have the ways we can get to this ancient energy, letting us go after resources that were completely out of reach before.
This slide just perfectly sums up the two main strategies. Conventional drilling is all about tapping the container. You drill straight down into that porous reservoir rock to get to the oil that's already pooled up. But hydraulic fracturing, or fracking, is a whole different ballgame. It drills horizontally, right into the kitchen, the source rock itself, and then it creates tiny little fractures to force out the oil and gas that never got a chance to migrate out in the first place.
So why on earth do we go through all this geological trouble? The answer is all about energy density. Look at this number, over 5.7 million. That's how much energy, measured in BTUs, is packed into one single barrel of crude oil. To give you some perspective, that's about the same amount of energy a person could produce doing manual labor for 10 straight years. It is an unbelievable concentration of ancient sunlight. And that really brings us to the final and maybe most important thought. The Earth's geology spent hundreds of millions of years slowly, patiently saving up all this energy. And our technology has figured out how to release pretty much all of it in what is, geologically speaking, the blink of an eye. And really understanding that incredible imbalance of time, well, that's the key to understanding our entire relationship with energy today.
Welcome to The Explainer. Today, we're digging deep into one of nature's most powerful events, the earthquake. We're going to break down exactly what's happening when the solid ground beneath your feet suddenly, and sometimes violently, starts to move.
To really get what an earthquake is, we have to look way, way down, deep inside the Earth. See, the story of a quake doesn't actually start with the shaking. It starts with this slow, silent, and immense buildup of stress in the planet's crust. It really all comes down to pressure. You've got these massive tectonic plates that are always moving, grinding against each other. And all that pressure has to go somewhere, right? It just builds and builds, sometimes for hundreds of years, until something has to give.
So here's the key thing to remember. The earthquake isn't the shaking itself. The shaking is just the result. The earthquake is that sudden, incredibly rapid release of stored-up energy. It's like a colossal firecracker going off miles beneath the surface. Now, when we talk about where an earthquake happens, seismologists have two very specific terms. You got the hypocenter, which is the actual spot deep underground where the rock slips. And then you have the epicenter. That's the location on the surface, on the map, right above where all the action started. It's usually what you hear about on the news.
Okay, so let's dive into how this actually works. A scientist named H.F. Reed came up with this idea after the huge 1906 San Francisco earthquake. He realized the only way the ground could move so far, so fast, was something he called elastic rebound. Think about it like this. Take a plastic ruler and start bending it. You're loading it with energy. If you bend it too far, what happens? It snaps back. That twang is the energy being released. Now just imagine that happening to a block of rock the size of a city.
So, all that energy that just got released, it doesn't just stay put, it has to travel. And it does so as these powerful vibrations we call seismic waves, which blast out from the hypocenter, kind of like ripples spreading out in a pond.
And these waves that travel through the body of the Earth come in two main flavors. You've got P waves, or primary waves. They're compressional, they push and pull stuff, and man, they are fast. Then you have the S waves, or secondary waves. They're slower, and they move side to side, shaking the rock, but check out that last row. S waves can only go through solids. And why is that? Well, think about it. You can't really shake a glass of water from side to side and have it snap back. You can't shear a liquid. This little fact turns out to be a massive clue about our planet.
But, it's kind of funny. You'd think the fastest waves would be the most dangerous, right? Nope. The waves that cause the most damage are actually the surface waves. They're the slowest, they arrive last, but they pack the biggest punch. They have this big, rolling motion that's just absolutely devastating to buildings.
All right, so we know what's happening, but how do scientists actually measure these massive, invisible events happening miles beneath our feet?
They use an instrument called a seismograph. And the basic idea is pretty clever. It has a really heavy weight that's isolated from the ground. So when an earthquake hits and the whole room starts to shake, that weight stays still, allowing a pen to draw out the vibrations on a rolling piece of paper. And because P waves are faster, they always show up first on that recording.
So that time gap, the lag between when the first P wave hits and the first S wave hits, tells you exactly how far away the earthquake was. The longer the gap, the farther the quake. But that only gives you a distance, not a direction. It's like me telling you something is 100 miles away. Okay, but in which direction? That's why you need readings from at least 3 different stations. You draw a circle of the right distance around each one, and the one single point where all 3 circles cross, that's your epicenter.
Now this is something people get mixed up all the time. Magnitude versus intensity. They sound similar, but they're totally different. Magnitude is one number for the entire quake. It measures the total energy released at the source. Intensity, on the other hand, describes what the shaking was like at a specific place. So a simple earthquake has only one magnitude, but it can have a whole bunch of different intensity values.
And this is where things get kind of wild, because the magnitude scale is logarithmic. All that really means is that for each whole number you go up, the actual ground shaking increases by 10 times. So a magnitude 7 quake isn't just a little worse than a 6. It shakes the ground 10 times more intensely. It's a huge jump. You think a 10-fold increase in shaking sounds like a lot? Well, hold on, because the total amount of energy that's unleashed is on a completely different level. The shaking might be 10 times worse, but the raw power behind it is, wow, it's just so much greater.
Yeah, about 32 times more energy for each whole number you go up the scale. So that means a magnitude 7 quake isn't twice as strong as a magnitude 5. No way. It releases over 1,000 times more energy. The power just skyrockets.
And all of that incredible energy, well, it has to go somewhere. And the results for us here on the surface can be absolutely devastating.
Of course, the shaking itself is the main danger, but that's just the start of the cascade. The vibrations can cause soil to basically turn into quicksand, a process called liquefaction. It can trigger massive landslides, break gas lines, and cause huge fires. And if it happens under the ocean, it can create catastrophic tsunamis.
And these events really bring it all home. They are these stark, tragic reminders of why this science matters so much. Understanding how these things work is the first step toward building better, safer communities and warning systems that can actually save lives.
But here's the twist. For all their destructive power, earthquakes have given us this surprising, incredible gift. They've given us a way to see inside our own planet, a place we can never, ever go ourselves.
Okay, let's go back to that crucial clue from earlier. Remember we said P waves can plow through anything, solid, liquid, gas. But S waves, with their side-to-side motion, get stopped cold by liquids.
Well, scientists started noticing this really weird pattern. After a big quake, they'd see S waves popping up on seismographs across the globe, except for in this one huge area on the complete opposite side of the planet. It was like something in the center of the Earth was casting a giant seismic shadow.
There was only one possible conclusion. That S-wave shadow could only exist if the Earth's outer core was a massive sphere of liquid, stopping those waves in their tracks. We basically gave the planet an ultrasound using earthquake waves. It's brilliant when you think about it.
And by studying exactly how these waves bend and bounce and change speed as they travel through the planet, we've pieced together the entire structure of our world's interior, from the thin crust we live on, to the solid mantle, to that liquid outer core, and right down to the solid iron ball at the very center.
So in the end, earthquakes are this humbling, powerful reminder. They show us that the ground beneath our feet isn't just some static, dead rock. It's a dynamic, living system that is constantly and powerfully reshaping itself. Earthquakes are both a hazard to be respected and an incredible key to understanding the very planet we call home.
Have you ever really, truly wondered what's going on right under your feet? And I don't mean just a few feet down. I mean thousands of kilometers deep, right to the very center of our planet. Well, today, we're going deep, literally, to figure out the incredible forces that are constantly shaping our world.
So let's start with the biggest puzzle of all. The deepest hole humans have ever drilled barely scratched the surface. Seriously, we've only made it about 0.2% of the way to the core. So if we can't see it, if we've never been there, how in the world do we know what's inside our own planet?
For the longest time, this was one of the greatest mysteries in science. I mean, the inside of our own homeworld was a total blank. But, just because we couldn't physically go there didn't mean we couldn't figure it out.
So, scientists started treating it like detectives on a cosmic crime scene. They couldn't visit the scene itself, but they could look at the evidence. And it all boiled down to two crucial clues that just blew the whole case wide open.
All right, so how did they crack this thing? Well, it didn't start with some fancy gadget. It actually started with a really simple observation, a puzzle that just didn't quite add up.
The very first clue was a total head-scratcher. It was this paradox of weight. Basically, the numbers just weren't making sense based on what scientists could see and measure right here on the surface.
See, when we measure the density of the rocks that make up the continents, the ground we're all standing on, you get a number that's around 2.7 grams per cubic centimeter. That's your typical crustal rock. Simple enough, right?
But here's where it gets weird. When scientists calculated the mass of the entire Earth, they figured out its average density is about 5.45 grams per cubic centimeter. That's nearly double the surface rock. All of a sudden, the math just doesn't work.
So this led to a really big question. If all the stuff on the surface is pretty light, where is all that extra mass hiding? The only logical answer was that something way, way heavier had to be lurking deep down inside, pulling that average way up.
Now, the second clue came from listening to the planet itself. You can kind of think of it like a giant natural ultrasound, a planetary echo that lets us see what's impossible to see with our eyes.
Okay, so every time there's an earthquake, it sends these super powerful vibrations, called seismic waves, zinging through the entire planet. And by tracking these waves all over the globe, scientists noticed something amazing. The waves didn't just travel in a straight line. Nope, they would bend, they'd bounce, they'd speed up and slow down. That told them that these waves were hitting distinct boundaries and passing through totally different types of materials deep inside the Earth.
So when you put those two clues together, the weight puzzle and the planet's echoes, you get one undeniable conclusion. Our planet isn't just one solid ball of rock. It's made of layers, kind of like an onion, with all the heaviest stuff packed right in the middle.
And this is what solves that mystery of the missing weight. The Earth as a whole is about 35% iron. And because iron is so heavy, most of it sank toward the center when the planet was first forming. That's where all the extra mass was hiding the whole time, in a dense iron core.
Now compare that to the crust, it's a totally different story. The crust is mostly made of much lighter stuff, like oxygen and silicon, with only about 5% iron. And that's exactly why the surface is so much less dense than the planet overall. The heavy stuff sank, and the light, frothy stuff floated to the top. So we figured out that the light stuff floated up and made the crust. But the story gets even cooler, because that thin top layer, well, it isn't all the same. There are actually two very different kinds of crust, and they're constantly interacting with each other.
On one side, you have the continental crust. It's thick, made of granite, and pretty light. That's what makes up our continents. But then you have the oceanic crust, under the oceans. And what's wild is that even though it's much, much thinner, it's made of a rock called basalt, and it's actually denser than the continental crust. This little difference in density, well, it's the key to basically everything that happens on the surface.
Because these different layers and these two types of crust, they aren't just sitting there. Oh no. They are part of this unbelievably dynamic system that keeps our planet's surface in constant, churning motion. And all of this brings us to the big one, plate tectonics. This is the theory that Earth's entire outer shell is broken up into these massive, rigid plates that are just sort of floating and sliding around on a hotter, gooier layer just beneath them.
And I'm not kidding, this isn't just a theory, it is the unifying theory in all of geology. It's the big idea that finally made everything else make sense. Ever wonder why earthquakes and volcanoes pop up in very specific places, like the Ring of Fire around the Pacific? Plate tectonics. It's at the edges of these plates where all the action happens. They grind past each other, they pull apart, they dive underneath one another, and all that movement releases incredible energy as earthquakes and lets molten rock erupt as volcanoes.
So there you have it. The clues from weight and echoes revealed a layered planet. Those layers create a system that drives the motion of tectonic plates, and that motion shapes our entire world. But this whole process isn't over. The continents are moving right now, at about the same speed your fingernails grow. Which leaves us with one last, mind-bending question to think about. What do you think our planet is going to look like 100 million years from now?
You know, when you see a volcano, it feels like this raw, untamable force of nature. But what if I told you its power, its location, even how it erupts? None of that is random. There's this incredible hidden system, a sort of global blueprint, running deep beneath our feet. It's a tectonic engine. And today, we're going to uncover the secrets of that engine and the fire it creates. All right, so here's the plan. First, we're going to look at this mysterious fiery ring on Earth. Then, we'll dive into the tectonic engine that makes it all happen. After that, we get into the cool part, magma's secret recipe. We'll see how that recipe literally builds a volcano's shape. And finally, we'll learn how to decode the dangers just by looking at them. Okay, let's kick things off in the Pacific Ocean. It's home to this absolutely massive chain of volcanoes called the Ring of Fire. And trust me, that is not just a cool name. It is the absolute epicenter of our planet's geological drama. And when I say massive, I mean it. Get this one single region holds about 75% of all the world's active and dormant volcanoes. Think about that. From the Andes, up through North America, across to Japan, down to New Zealand, it's this huge, almost unbroken loop of fire. So you gotta ask, right? Why here? Why isn't this more random? Why are they all clustered in this one giant ring? There's clearly a secret the Ring of Fire is hiding, and we're gonna find it. Well, the answer, as you might have guessed, is deep, deep underground. It all comes down to the basic mechanics of our planet, plate tectonics. The idea is simple. Earth's crust isn't one solid piece. It's broken up into these gigantic moving plates. And it's how these plates crash and grind and pull apart, that's the engine that builds every volcano. So this tectonic engine, it really has three main settings. First up, collisions. You get one plate forced down under another, that's called subduction. The plate that goes down melts, and that molten rock has to go somewhere, so it rises up and creates volcanic chains like the Andes. Okay, second setting. Plates pull apart. This creates a huge gap, and magma from below just rushes in to fill it, forming massive mid-ocean ridges. And then there's the third way, which is super cool, a hot spot. This is basically a blowtorch of super hot material from the mantle that just punches a hole right through the middle of a plate, creating island chains like Hawaii. But here's where it gets really interesting. The location, whether it's a collision or a hotspot, doesn't just tell you where a volcano will pop up. It actually determines the magma's secret recipe. And believe me, that recipe is everything. It's the #1 thing that dictates how a volcano is going to behave. Let's break it down with a simple analogy. Think about lava. You've got two basic types. On one hand, you have fluid, runny lava, kind of like warm honey. On the other, you've got this thick, sticky, pasty stuff. The game-changing ingredient here, it's a compound called silica. The rule is simple. Low silica, you get runny lava. High silica, you get sticky lava. Now, there's a sciencey word for the stickiness. It's called viscosity. It's just a measure of how much something resists flowing. So for our magma, it's pretty straightforward. High viscosity means it's thick and slow and likely explosive. Low viscosity means it's thin and runny and way more gentle. And this chart really lays out the two extremes perfectly. You've got basaltic magma, see how it's only got about 50% silica, it's hotter and has less water. That whole combination makes it super fluid, low viscosity. Then you look at the other side, granitic magma. It is packed with silica, like 70%. It's cooler and holds way more water. The results? It's incredibly thick and sticky. So when you're trying to figure out how violent an eruption is going to be, it really comes down to three things. 1, the magma's composition. Remember, high silica means it's sticky. 2, temperature. Hotter magma is always more fluid. But the third one, this is the real kicker, dissolved gases. That thick, sticky, high silica magma is amazing at trapping gas. It's like a cork in a champagne bottle. As that magma rises, the pressure just builds and builds and builds until, boom, a catastrophic explosion. It is literally like shaking up a can of soda and then popping the top. And this magma recipe, it does more than just decide how big the boom is. It actually sculpts the volcano itself. I mean, over thousands and thousands of years, the type of eruption literally builds a very specific, very recognizable shape. It gives the volcano its true identity. All right, first up, let's talk about the composite volcano. You might also hear it called a stratovolcano. This is the one you picture in your head, that classic, steep, almost perfectly symmetrical cone. It looks beautiful, almost like a postcard, right? But that beauty hides a very, very violent personality. And their shape comes directly from that thick, high-viscosity magma we were just talking about. The lava is so sticky it doesn't flow very far, so it just piles up layer after layer of lava and ash, creating that steep, iconic cone. And because that magma traps so much gas, their eruptions are, you guessed it, incredibly explosive. When you think of Mount St. Helens or Japan's majestic Mount Fuji, you're picturing a composite volcano. Okay, now let's do a complete 180 and talk about the shield volcano. These things are the gentle giants of the volcano world. In fact, they're the largest volcanoes on the entire planet, but you might not even realize you're on one. They are just that massive, that broad, and that gently sloped. And the reason for that unique shape? You got it. It's all about the magma. Shield volcanoes are built from that runny, low-viscosity basaltic lava. So when they erupt, the lava just flows and flows for miles in every direction. It slowly builds up this huge, wide dome that kind of looks like a warrior's shield lying on the ground, hence the name. The eruptions are way less explosive. It's more about these steady, fluid lava flows. The Hawaiian Islands, Mauna Loa, Kilauea, they are the poster children for shield volcanoes. So, okay, we've got explosive cones and we've got gentle giants. Why is this distinction so important? Because if you know the type of volcano, you can start to decode its specific threats. And let me tell you, the dangers go way, way beyond just hot flowing lava. Let's start with one of the most terrifying things in all of nature, and it's pretty much exclusive to those explosive composite volcanoes. It's called a pyroclastic flow. Just imagine a superheated avalanche, not of snow, but of ash, rock, and gas, that just roars down the side of a mountain. There's a French term for it, nuée ardente, which means glowing cloud, and for very good reason. And what makes them so incredibly deadly is the speed. We're talking up to 200 kilometers an hour. That's about 125 miles per hour. There is no outrunning it. They are completely unstoppable and just incinerate absolutely everything in their path. Another huge danger is something called a lahar. Basically, it's a volcanic mud flow. Picture this. Hot volcanic ash instantly melts the snow and ice on a volcano's summit. Or maybe it just mixes with heavy rain. Either way, you get this destructive slurry that has the consistency of wet concrete, and it just barrels down river valleys at high speed. It can bury entire towns miles and miles away from the actual eruption.
But not all volcanic dangers are hot and fast. Some are silent and just as deadly. Take the chilling story of Lake Nyos in Cameroon. Back in 1986, this volcanic lake, it just burped. It released a massive, totally invisible cloud of carbon dioxide. And because CO2 is heavier than air, this cloud just flowed silently down into the nearby valleys, pushing all the breathable air out of the way. It suffocated over 1,700 people and thousands of their livestock in their sleep. A true silent killer. So what's the big takeaway here? It's that a volcano's shape is its life story. A steep cone tells a tale of violent, explosive eruptions. A broad shield speaks of long, gentle flows. And that brings us to the final, crucial question. If a volcano's shape tells the story of its past eruptions, what warning is it giving us about its future?